Hi everyone. Today I'd like to talk to you about this. The title of the talk is encrypted. Let's apply the decryption. Okay, that's better. Mastering Cryptography Fundamentals with Node.js's crypto module. So let's break it down. What is cryptography? This is the study of or the science of means of secret communication. Now, inside of Node.js, we have a built-in module for handling cryptographic operations and algorithms. It's one of the built-in modules just like FS, so you can start using it right away. No need to install anything. It's built on top of OpenSSL, which is the widely used library for handling all types of cryptographic operations. Now, because it's one of the built-in modules, it has official documentation in the Node.js website. But in my personal experience, when I knew that I needed to use something crypto-related in a project, and I went to the docs, I found that, for me at least, it wasn't the best place to start. Because unless you're already kind of super familiar with cryptography and what type of algorithms are out there and in which use case you would use each one, this documentation is not the best place to start because there's no real structure there. It's a flat list of alphabetical list of APIs, and you kind of already have to know what you're looking for it to be useful for you. Luckily, we have other resources out there to learn about cryptography. For example, Yoni Goldberg recommended this book to me, and I thought it was really good. This is called The Code Book. And it doesn't only cover the history and the major concepts in cryptography, but it does them in the historical context of when those achievements in cryptography played an important role in our history, in geopolitical struggles and stuff like that. For example, you can learn about Alan Turing, who we know as the father of computing, but he was also a World War II codebreaker and was able to decipher the code that the Germans were using. And they say that this achievement helped end the war a few years earlier than otherwise. So for this amazing achievement, he is now immortalized on the 50-pound banknote. And I think this is really cool because, yes, he did amazing things that we would probably never achieve. But in a way, he was also a programmer, just like one of us. And I'm just imagining somebody, just a normal programmer, maybe giving a talk at NodeTLV and then having his face be on the currency. I think it's just an amazing thing. So the resources are out there. You can go and you can learn about cryptography, and then you can come back and see how those principles are applied in a practical APIs that you have inside the crypto module. But this is what I want to give you guys a shortcut through today. So that's what we're going to try to cover. We're going to go through the basic concepts, but also make sure that we see how they're exposed in practice as part of the crypto module. My name is Yonatan Mevorach. I'm a web developer from Wix, from the DevTools group, where we build developer tooling for the developers in Wix and also open source. This is where you can find me online. So let's get started. The first topic that we're going to cover today has to do with encryption. And to illustrate this, we'll use an example and throughout the talk as well with this couple, Alice and Bob. They want to communicate with each other. And they're going to do it over a channel which they know that they can't really trust that only they are listening because they're using an open channel like networks and the internet. And so they're going to have to assume that there's going to be other entities on the network, other people who can read what they send back and forth. For example, we have Eve, which sits somewhere on the network and can read all of the messages that are being sent across. So they have to find a way to still communicate securely, and this is what they will use encryption for. For this type of encryption to work, they need something which is called the key. We'll give an example of what we use as the value of the key in a minute. But the important thing is that the key should only be known to both of them. Otherwise, other parties can read what they're sending across. So they both have to have the same value, the same key, and only them. This means that in order to decide on which key they will both use, they will need to do this over not an open channel, a secure channel or completely offline. But this is the prerequisite for this type of encryption. So let's go over not exactly how the encryption will work, but we'll start with this as kind of a mental model to start with. So Eve has the text that she wants to send to Bob. This is called the plain text, the original text. And she computes the ciphertext. She does this with the key. For example, if the message is NodeTLV, then the ciphertext comes out something that just looks like gibberish. And this is what is sent over. So if Eve is there to read the message, no harm, no foul. And then Bob, in order to decode the message, uses his key as well, which has the same value. And then he's able to read the original message as well. So this is how we expect it to work, but let's talk about some real-world concerns before we see this applied in Node.js. And the first thing is the encryption algorithm itself. All these encryption algorithms work by substituting and transforming our original message, the data in our original message, but we have more than one. In fact, we have many different algorithms inside the Node.js crypto module that we can choose to use. And this is actually the first code from the crypto module that I'm showing today. So this is the get ciphers function. And as the name suggests, it returns a list of all of the cryptographic algorithms that are available on your machine. For example, on my machine, it returns 171 different algorithms that I can use. In our example today, we're going to take a look at AES, which stands for Advanced Encryption Standard, which is a widely used standard. Specifically, we're going to use AES 256 CBC. 256 stands for the length of the key in bits, and we'll talk about CBC in a second. But this is something that they need to agree upon. So either when Eve is doing the encryption, she will send the name of the algorithm as part of the message, and then Bob can know that he needs to use that for decryption. Or to begin with, when they set up the key, they say that let's always use this algorithm, but you can't encrypt with one algorithm and decode with and decipher with another algorithm. So we mentioned before that we're going to use a type of encryption which uses CBC mode. This stands for cipher block chaining. And this means in broad terms that when you want to do the encryption, you take the message and you separate it into blocks and you encrypt each block individually. In order to compute the very first block, you need to pass something which we call an initialization vector. And let's talk about the value that we give this. So this is how the encryption looks now. We have the plain text and the key as before. And as the IV, Eve needs to pass a completely random value. And this will have an influence on the value of the ciphertext. This means that even if every morning Eve sends hello, the same key and the same plain text, she will use a different IV every time, and therefore the ciphertext will be different. This helps make our encryption more secure because it removes any relationship between the original plain text and the ciphertext, which an attacker can try to analyze and break our encryption. So now, though, it means that Eve needs to send the IV as part of the message because Bob will need to use the same IV value for the decoding. Let's see how we actually do this encryption with Node.js. So this is Eve's code. First, as we mentioned, we need to decide on an algorithm, which we already did. We take the plain text message, which we convert from a string to a buffer, because we don't work with strings with the crypto module. In order to generate a random IV, we can use the random bytes function, which is also available on the crypto module. Eve loads her key into memory. We'll talk about what the key is exactly in a minute. And then we're ready to actually perform the encryption. We create a cipher object using the createCipherIV function. And then we can pass to it the plain text using the update method. You can see that we can call update many times. In this case, we don't need to because we have just a short plain text, which we already know in one go. And then to wrap up, you have to call final to get the entire ciphertext, which you can send over. Then let's take a look at this from Bob's side. In order to perform the decryption, he gets the IV, the ciphertext, and the algorithm. He loads his key into memory. And then you can see that this API looks very similar to the API that Eve used, but this is create decipher IV, which we use for the decryption. And again, very similar looking API, passing in the ciphertext to get back the plain text. One thing I wanted to note, up until now, we only mentioned that the key is something that they should both have, but we didn't explain what exactly the key should be, so let's talk about that. We might be tempted to use a human memorable password as the key itself, but this will make our encryption less secure. If we have a key size of 256 bits, it means that the size, the amount of options that we can have as the key is an astronomical number. But if we only limit ourselves to human memorable passwords as the key, this gives our attacker an advantage or an edge which they can use to break our encryption. Because it means that they don't have to try, if they're trying to brute force their way through all possible key options, they would only have to try a much narrower limiter set of passwords that humans use, even if they think they're being clever by changing O's into zeros and stuff like that. So we need to do better. But what can we do if we still want to rely on a password? So one solution to this problem is to use something which we call KDFs, key derivation functions. And we're going to see how they can help us still use a password as the root of the key of our encryption, but avoid this problem of having a very narrow set of options as the key. So KDF works like a hash function, which you may be familiar with from doing file integrity checksums and stuff like that. In that it's a one-way function and it's deterministic. Given the same input, will give the same output. But unlike a hash function or most functions, it's actually designed to be slow. And the reason is we want it to be slow but good enough if Eve enters her real password and wants to get the value. But for an attacker trying to loop through and try all the most common used passwords and seeing their key output, it will take them a long time because this function is made to be slow and also memory intensive. So this is an improvement, but if you think about it, there's still a problem here. Because even if this function, each iteration takes like an hour to run, the attacker will only have to do this once. What the attacker can do is go and find or compute this themselves, a list of all the most commonly used passwords, and the output that you get when you run them through the slow KDF. And then it defeats the entire purpose of having this, because they can just loop through all of these values instead, the values on the right. So to make this harder for the attacker, what we do is we add another input to the KDF, which we call the salt. And this is, again, a random value. And this means that even if the attacker has access to the salt, in order to derive the key, they would have to, again, recompute all the most common used passwords using our particular salt, which we hope will make it not worth their while because it will take too long. So let's see how this affects the encryption process. In order to derive the key, Alice takes her password, which she remembers, and the salt, which is a random value. She gets a key value. Bob needs to use the exact same salt value in order to get the exact same key. And the rest of the process is as we showed before. Let's take a look at this in code. We have a KDF baked into the crypto module, which is called script, secure crypt. And given a password, which you load, and then, again, generating random bytes as the salt, you pass that to the script function, and you get the key, and you use it in the rest of the encryption process as we showed before. And on Bob's side, pretty similar. He doesn't need to generate a salt. He uses the same salt and gets the same key. Other notable mentions here, we have two other KDFs inside the crypto module. We have HKDF and PBKDF2. Today, KDFs are mostly used for password storage. So as we can see, generating random data is very important to doing secure cryptography. So we have a first rule of generating random numbers for cryptography, and that's don't use map.random, because as the MDN docs state, it is not cryptographically secure, which means an attacker can either guess what this returns or inject something in your machine so it will return something which the attacker planted there. So just don't use it. Luckily, we have other ways of generating random data inside the crypto module itself. All of the async APIs here are callback based, so you need to call promisify on them if you want to work with promises. So let's go over them. We already saw random bytes, giving a number of bytes, return a buffer of that size with random data inside. We have random fill, which takes an existing buffer and either fills all of it or a subset inside with random data. This is a great time to update Outlook. Thank you. We have random int, which given a min and max value returns an integer in that range. And we have a random UUID. Okay. So if you think about it, the weak link in the encryption process that we showed so far is the fact that Alice and Bob had to exchange and agree on the key outside of the secure channel that they were using to communicate. And if Alice and Bob represent computers, which I hope you figured out by now, then it's not really feasible, because every day our computer is talking to new computers on the other side of the world. We don't have an off-way line of agreeing on keys that we will use for encryption. So we need a better solution. And this is something that Eve thought long and hard about. And honestly, I did too. And in fact, this is something that was known for many years as a problem, which is called the key distribution problem. Luckily, in the 70s, a group of 3 scientists from MIT published a solution to this problem. The algorithm is called after their initials, RSA. So let's see how this is done. We have 2 keys for Bob. He needs to generate 2 keys, his private key from which he can derive his public key. The public key is made known to the world, but he keeps his private key private. If Alice wants to encrypt a message and send it to Bob, she needs to take Bob's public key and uses that as the key for encryption. She sends a ciphertext to Bob, and then Bob, to decrypt, uses his private key. So if before we were using the same key for encryption and decryption, now we're using one key for encryption and another for decryption. This is why we call this asymmetric encryption. Let's see how this is done in code. First, to generate the key pair, Bob can use the generate key pair function from the crypto module, which already generates the 2 keys. He has access via the public key property to the public key. He can export it and share it with the world, and he can save the private key to file and keep it private. Now, in order to perform the actual encryption, what Alice can do, first she loads Bob's public key into memory with the plaintext, and then she can call public encrypt in order to perform the encryption, passing in Bob's public key, the plaintext message, and she also needs to configure which type of padding to use. Padding is something which helps introduce randomness into the process and also make sure that the size of the resulting ciphertext has no relationship with the size of the input plaintext, which is another way to make life harder for our attackers and code breakers. Then on Bob's side, in order to perform the decryption, he loads his private key into memory, and he uses the private decrypt method in order to perform the decryption, passing in his private key, the ciphertext, the same padding definition, and he will get back the original plaintext message. Now, as I mentioned, this algorithm is RSA, which was published, but we have to mention that before this, a different group of scientists from Stanford University published a different type of solution to the key distribution problem, which is called the Diffie-Hellman key exchange, which I encourage you to read more about, and is also available as part of the crypto module. And there's another algorithm available named after the same group. This is elliptical curve Diffie-Hellman. ECDH, and this is, I would say, more widely used today. So now we're feeling better about the solution. We've come a long way, but as Alice shows here, we still have a problem. Because using this type of cryptographic public key system, anybody in the world can send Bob a message, but how can Bob know that the message really came from a certain entity that claims that the message came from them? So to give this example, let's assume that Alice is one of the organizers of NodeTLV. She wants to send Bob a free ticket. He should be able to walk up to the front door of the conference and just say, please let me in. I can prove that Alice wants me to go in. If there's no way to verify that the message came from Alice, nobody's going to let him in. So in this process, we're going to be using signing and verifying. This is how the signing process will work. Alice uses her private key and the message. In this case, the message itself is not encrypted. It's fine if anyone can read it. And using it, she computes the signature, which looks like a hash value. It's just, it looks like random values. And then she's able to send the message and the signature to Bob. Her public key, as is customary in this type of system, is known to the world. And then what Bob can do to prove to himself that the message really came from Alice, or if he wants to prove it to somebody else, he can take Alice's public key, the message, and check the signature. Only someone with access to Alice's public key can create a signature that can be verified using Alice's public key, and this is why this proves that the message came from her. Let's see this in code. So in order to perform the signing, Alice will read her private key into memory, take the message that she wants to sign, and call the crypto.sign method in order to do that. She needs to specify the hash function to use as part of this process, the message itself, and her private key. Over on Bob's side, to perform the verification, he will read Alice's public key into memory, and he will use the crypto verify function to do the reverse. You can see that every time the other party uses a very similar API to the other side. So the parameters are pretty much the same, but he also needs to pass in the signature, which we want to verify. And this will only return true if indeed the math checks out and the signature matches the keys used. Other notable mentions here, we have something called a hash-based message authentication code, or HMAC for short. This is another type of solution to authenticating and making sure that some party was involved in the input that you get, but more in the worlds of a symmetrical encryption. You can read more about it in the docs, of course. Now, some of you might be wondering right now, this stuff is pretty cool. I mean, we know that everything that is inside the crypto module is based on OpenSSL, which we use to set up like TLS connections. So obviously this stuff is useful if you're implementing TLS, but we don't get to do that in the day-to-day. So when do we get to use this stuff? So to answer that question, I want to take you back just 2 years ago, when in order to go into a coffee shop or restaurant, you had to do this fake dance with the person at the door, where you showed them the QR code that shows that you're vaccinated. Now, they never actually bothered to scan it, so it didn't matter if it was just a link to a Rickroll video. But at least in theory, the idea behind it worked. So this is a protocol by the EU for proving that you are indeed vaccinated. And what the QR codes contained is not an encrypted, it's not your encrypted vaccine information. It was actually human readable, plain text, JSON object. This is who you are, when were you vaccinated, and what type of vaccine you got. But it also included the signature. And the signature was done with this signing and verifying private and public key system. So only the Ministry of Health here in Israel can sign and create this signature, but actually their public key was published and made available on their GitHub. So anybody can go and create an app that works offline that can scan the QR code and verify that you are indeed vaccinated. Okay, so now we go back to Alice. Is she happy with the system that we came up here, that we showed up until now? Are there no weak links? Well, we put a lot of emphasis on trusting someone because we know that they publish some public key and they say, this is my public key. So now this is the weak link in our system. If somebody is saying, this is my identity and this is my public key, and it's not actually that person, then we kind of lose trust of the whole system. And this is what we solve with certificates. Certificates say, this is who I am, this is something that you need to know about me, and here's a signature that proves that. And I'd like to make a point about how we should trust certificate by showing you a certificate that I got. This is a certificate from the creator of Git for never having to Google how to run Git commands, never being confused, never having to go on Stack Overflow. And you can see there's a signature there, so you can tell that you can trust it. Luckily, in cryptographic certificates, we can actually verify the signature. And it's important that we actually do that. But I should also say that there's no real magic solution to how we can trust that someone says that this is my public key. The only thing that we kind of can do is find a shared party that we both trust and say, okay, if this entity trusts that entity, then I guess I can trust them as well. In the case of Alice and Bob, what they will do is they both know Carol, which, as you can tell, is Bob's sister, obviously. And she's also a friend of Alice. And then if they both trust her, then the system will work. Let's see how. So Alice will want to create her certificate. She will take her public key, which is the main thing that she wants to establish ownership of. And she will add to it different metadata about herself, her name, her country, stuff like that. This is a list of data which we call TBS, to be signed. And she will create a certificate signing request and send this to Carol, who wants to help out with helping validate that this is indeed Alice. So similar to the signing and verifying process we showed earlier, Carol would take her private key and create a signature based on the message, which is the TBS. And Alice will take Carol's signature and will put that as part of her certificate and share it with the world. Anybody who trusts Carol can now trust Alice. Bob won't trust the certificate. He will perform the verification. So he will take Carol's public key and, again, similar to before, validate the signature using Carol's public key. And then he can know that if this checks out, then he can trust that this is indeed Alice's public key. Let's see how we can perform the verification in code. Bob reads Alice's certificate into memory and creating a X509 certificate. That's the name of the standard. We can read the metadata on the certificate. This is the subject, Alice, and Carol. We can check the range until when the certificate is valid. And then to crucially actually perform the verification, he can read Carol's certificate into memory, which has Carol's public key, and perform the verification. And this will return true if all the math checks out. So how can Bob trust Carol? Well, of course, how do you trust your sister? You have to trust your mom first. So this is Doris. The point I'm trying to make here is that this is something that we call a certificate chain. You want to communicate with someone, they show you their certificate, you go through their certificate, and at the end you reach a certificate that you can't validate with anyone else. If we go, for example, in Chrome to view the certificate for the Node.js website, at the very top there's a certificate that you can't trust using a different certificate, and this is because it's baked into your operating system. So we covered the fundamental concepts in cryptography. You're now experts. You get a certificate signed by Alan Turing, so you know that it's legitimate. This is where you can find all the code samples I showed you today. I will post this on my Twitter if you want to check it out. I write about cryptography. I write about other projects. Recently, I turned an arcade machine into a Grafana monitor, if you want to read about that. And if you have any questions, you can find me later in the conference, but I won't be able to help you. I don't know much about cryptography, but I brought Alice, Bob, and Eve with me. Maybe they can answer your questions. Thank you.